Hello, good afternoon. Today we talk about application of theory of shock waves and expansion waves. Is the first question which we will discuss, and the second question, I think we have enough time to start talking about model of flow in a nozzle, subsonic and supersonic flow in a nozzle. Okay, last time we had the discussion on calculation of properties of flow after oblique shock wave and the expansion wave. We saw that these two type of flows are combined one with another. When, for example, shock wave happen, we can always observe after expansion wave and vice versa. Applied to a real structure, Anderson gives us example presented at the end of chapter 9 about calculation of tail and optimization of geometry of tail, which is having a purpose to control flight. Okay, this tail can be seen on figure 38. It's a conical wedge of 10 degrees, opening angle, quite sharp body. And now we will see why it's better than just a flat plate. If we see initially and compare flat plate with the wedge, conical wedge, it looks like just a plate would be better from point of view of performance, right? If it will be smaller, it will be thinner, much thinner structure, could provide better value of controllability, but is not, as we will see later. What is controllability for us? Well, controllability is a side force which is created by this wedge and which allows to make a lift. It's called the lift force in one or another direction. Okay, drag force here is not considered because it's not the main purpose of this wedge. Since angle is 10 degrees, this drag would be small with respect to lift. And of course, with our theory of shock waves and expansion waves, we always can find value of this drag. This particular example concerns only about calculation of lift force or side force created by tail when we change angle of attack. So here is initial data. For example, 913, we have two different geometries. We have flat plate, case A, and this is infinitely thin flat plate, and we have Mach 7, which our aerodynamic body is flying, and 10 degrees angle of attack. 10 degrees inclined tail, so it creates some certain value of lift and lift coefficient. And we have case B on the right side of this slide, which is composed by wedge of 10 degrees, and it's symmetric. And also it has Mach 7 and 10 degrees angle of attack, so same boundary conditions for flow. And here, using theory of shock waves and expansion waves, we can calculate forces acting on this wedge from sides. We know that forces on upper and lower side will create for us necessary lift control force. Case A with the plane. I put here some calculations from book. We may see here. Okay, just a moment. I will see what if we have some. No, it's okay. So case A calculation of this wedge is consisting of two parts. part which devoted to calculate upper part Prandtl-Meyer flow. For this, first for Mach 7, we obtain angle of Prandtl-Meyer function, okay, and then we summate this angle of Prandtl-Meyer function with angle of attack and obtain Prandtl-Meyer function when flow is changed. So we have M1 here and we have M2 after change happens at this same volume where we need to calculate pressure. We need Mach number because we will use isentropic relation. Since flow is isentropic, we can calculate pressure drop as a function of Mach number. So this Prandtl-Meyer function is here. According to this Prandtl-Meyer function, we find Mach number. Okay, it can be done analytically or can be obtained from Appendix C. And we see that Mach 956 we have in region 2. And then using the entropic relations or Appendix A, we calculate pressure drop on transition from infinite to region 2. For this, we are using pressure drop with respect to stagnation pressure. Since our flow is isentropic on the upper side, this transition is isentropic, we use same stagnation pressure also for region 2. Taking these functions or calculating these functions from theory or using Appendix A, we obtain ratio between static pressure, pressure 2 and pressure 1. We see that pressure 2 is approximately 8 times smaller than pressure 1 or infinite pressure. So we calculate this upper part of pressure, then when we multiply this to projection of our body on horizontal axis. Okay, I will make some small drawing here. So when we make projection, we will need to take this size. Okay, it will be equal how much? Depend on the size of chord we will denote here. And so we have alpha 10 degrees. First is next is calculation on the lower side before we calculate lift and lift coefficient projection. We use theory of oblique shock wave for lower side when flow passes below. It's okay, not so much correct to draw like this. More for subsonic case. For supersonic case is different. We have constant velocity direction before shock wave, and we have flow direction equal to inclination of surface after shock wave. So this is correct streamline. Okay. And for previous case, I would like to remind you that flow is inclined in a similar way. It's horizontal before Mach angle, mu1. Then flow starts to incline. Then it stops to incline when we reach second Mach angle and continues to be parallel to a wall, like this. I try to make my best in this drawing. Hope it's clear. So for lower side calculation, we need to use theta beta m relation or diagram from book, figure 9.9, and for Mach 7 and 10 degrees of angle of attack, we find beta angle 16.5 degrees. Then using this angle of shock wave, this beta angle is exaggerated, of course, here because it's not in scale. Okay, but this beta angle, if I extend is here, beta, 16.5 degrees. Now using this beta angle, we calculate normal component to of Mach number to shock wave, and it's 199. Okay, always remember that should be supersonic because only supersonic flow can create shock wave. Even normal component of this shock wave should be supersonic. And then using appendix B for this Mach number, we are searching for pressure ratio. By appendix B or by formula presented in the book, we can find pressure ratio between flow behind shock wave and before shock wave. It's 4.45. So our pressure on the lower side of airfoil is more than 4 times bigger than infinite. Okay. Then we define lift coefficient. Lift coefficient for compressible flow. We already saw this before. Formula here, cosine alpha, is giving us projection on horizontal axis. So when alpha is 0, it means that all force is, we can use all area as projection, right? When alpha is 90 degrees, we have no projection area on horizontal direction. Okay, and inside lift coefficient formula, we have Mach number, adiabatic constant, infinite Mach number, and adiabatic constant, and our pressure ratio is calculated for the lower and upper side of plate. This CL formula we already had before in our lectures and also in Anderson book. We may find how it's received from original definition of lift coefficient for compressible flow. So if you have questions how this formula, why this formula appeared here, we can find it in our previous discussion or in previous pages of book. And then substituting all known parameters, we obtain lift coefficient 126. Not so big lift coefficient, right? When we compare this lift coefficient, for example, to airfoil, which for 10 degrees could have lift coefficient around 1, okay, for airfoil. It's CL near 1, okay, for this angle of attack. But for just flat plate, it's approximately 8 times smaller. Why so different? And lift coefficient for airfoil and for plate. This is why we need to study aerodynamics, because simple aerodynamic body, as we know, never provides sorry, a very good performance of our body. Okay, just a moment. I'm trying to see if there are some questions. No questions for now. I remind you could ask your questions in chat or by voice. Do not forget. So flat plate provides very low lift coefficient, but this lift coefficient is quite big with respect to 0, right? Because lift value is big, because when we have so huge value of Mach number, lift force will be also very, very high, very high. Okay, because once we calculate the lift force, I remind you, we need to multiply by velocity and square. For this case of Mach 7, it's approximately 2 kilometers per second. So we multiply lift coefficient by a very big value when we receive lift force. So having low lift coefficient does not mean that lift force will be small. No, lift force will be huge. So this is why, one of the reasons why maximum angle of attack can be 10 degrees. It cannot be bigger than 10 degrees because it's not required so huge force. But still, I think lift coefficient could be better, could be bigger, right? We see it comparing with the airfoil, and the next design of tail based on wedge is showing to us that optimizing geometry or using, instead of plain a wedge with a small angle of opening, we can have much better result. Okay, please do not forget that also here we have possibility to calculate drag and drag coefficient. We just need to make projection on other axis, on horizontal axis, and instead of cosine alpha, if we use same formula but with the sine alpha, we can receive CD coefficient. So in such simple way, and the lift to drag ratio will be cosine divided by sine. So it's cotangent of alpha is given to us lift to drag ratio. It's constant, independent on Mach number, and just depends on angle of attack. Okay, so I will probably write down here that lift to drag ratio would be cosine by sine alpha, or cotangent of this angle. Quite simple, right? Independent on geometry, independent on lengths, independent on Mach number. We can find it in a such way. No, maybe they probably dependent on Mach number, because calculation of oblique shock wave and expansion wave depends on Mach number, but not directly. Not directly. For this particular value of angle of attack, it's just a ratio between angles of attack. Right? But the base is also a function of Mach number. And this general part is a reaction force action, which we split into components. So let's see case B, where we have two calculations to make. We have same part for wedge. First, the upper part, as before, flow structure is very similar. We have Prandtl-Meyer function, same as we had before, and we add the 5 degrees, not 10 degrees as in case of plate, because we have inclination of upper surface just 5 degrees. Okay, it's 15 total, or 10 degrees angle of attack, and minus 5 of one half of this edge inclination of with respect to axis of wedge or central line of edge. Okay. So this is why we have just 5 degrees. We are using 5 degrees because this small angle here is 5 degrees. Then we obtain from this Prandtl-Meyer function our Mach number, which is 8.1. We can compare it to our previous calculation. We had 956. So Mach number for wedge is smaller. This is obvious because angle of body inclination is smaller, so the acceleration is also smaller. Smaller disturbances in flow result in smaller acceleration of flow. So 8.1, and then by same logic as before, we obtain pressure values. Okay, just a moment. I will see where is where is here is explaining how we make projection of forces on our axis. We use our trigonometric function, right? Length is horse divided by cosine of 5 and theta. Just a moment, I'm trying to find where pressure is defined. We have P02 by P2 is relation on stagnation pressure and relation on length, and also relation on stagnation pressure at entrance. And then we obtain force. Okay, we obtain force. So will be calculated based on forces, such lift coefficient, not just based on pressure and projection of pressure. Here in example B, Anderson gives to us another way of calculation of pressure coefficient when we, instead of using just pressure and projection, we calculate force and then extract one force from another. And same way we are in the same way we are calculating oblique shock wave above our above on the lower side of our wedge. We have Mach 7, theta 15 degrees. From Mach and theta we obtain beta inclination of shock wave. Before we had a smaller value also. Let's see how much it was. It was 16.5. Now it's more than 20. Now it's 23.5. So shock wave angle is bigger, and it means that our pressure rise will be also bigger. Okay, so we have this normal component of Mach number more than 1. And using Appendix B, we calculate pressure ratio at this normal component of Mach number, and we obtain 8.9 times approximately rise of pressure on the lower side. 8.9 times is bigger than we had in our previous case, because here we have more stronger shock wave. So before we had 445, here we have almost nine times. So pressure is much higher in case of wedge, mainly because we have not 10 degrees as an effective angle of inclination of flow, but we have 10 plus 5. We need to add this symmetric angle to obtain inclination of lower edge. So in total, we receive 15 degrees. This is why on 15 degrees we have bigger value of pressure ratio. And then we obtain forces on the lower part. Right, force is proportional to pressure, proportional to length, as we know. And then we subtract these forces one from another. Here we have a lift force, which is difference between upper and lower force. It's absolutely same approach as I told you from case A, but instead of pressure and projection, we calculate force directly here. So this is reaction. Oh, sorry. Reaction and projection here. It's also reaction and projection here in a very, very similar way that we had before. So logic is absolutely same. At the end, we find lift force in a such way. It's approximately proportional to 8 times of pressure multiplied by length of wedge. And then calculation of lift coefficient by standard formula, which we know from aerodynamics, right? Lift coefficient is lift divided by Q and C. In such case, we calculate Q from dynamic pressure, knowing Mach number, and pressure from our previous definition, right? Let's see how much it will be. That probably Q would, or Q1, okay, Q1 at section 1 would be how much? Gamma divided by 2. Pressure 1 Mach number 1 in square. This formula I also remind you we had before, so please do not forget that all formulas that appear then happen not first time in this example. You can find them in our previous discussions. So we calculate lift coefficient based on this formula, and we obtain 0.241. Of course, also smaller than 1, we never can obtain lift coefficient high value, like for airfoil is 1, right? So but in this case, we have lift coefficient approximately 2 times bigger than for just a plate. So we had 0.126 and now 0.241, almost 2 times bigger lift coefficient. For us, it means better controllability or smaller angle of attack for same value of control force, or to need to use 2 times smaller size of wedge for creation of same control force. If we have smaller tail, it's an advantage because smaller tail means smaller weight, smaller drag, right? If we have a smaller angle of attack, it's also an advantage for same tail because smaller angle of attack, it means that it will be controlled much faster. So response time will be much better. So a lot of advantages, just change in geometry of tail from flat plate to a wedge of calculated geometry is obvious disadvantage. Of course, it's another question, how big should be angle of wedge? Should be 10 degrees or should be 7 or 12 degrees? To answer this question, should be analyzed necessities, right? And available resources on the airplane. I mean, if we have enough power to have bigger angle of a wedge. Of course, when you have bigger angle of wedge, you create bigger value of control force, but same time you increase value of drag. So you need more power of engine for such flight. So there is always a balance between necessities and what we really can provide possibilities. This is, I think, very, very interesting, very important question. Please let me know if you have question on this example, which I just showed you. Okay. Probably there are no questions. You can read more in details about such project, and about development in the books. There are a lot of sites or materials distributed by NASA. It's NASA project, very popular and advanced. So for people who are interested in area of hypersonic flow and optimization, could be very useful such information. Our second part of today's discussion, let's say second part of first part, because then I would like to present another topic, is interaction between shock wave and the boundary layer. We already know that analytically it is possible to calculate reflection of shock wave from wall. We already saw how to make such calculation when shock wave hits the wall. when our impacts wall, we can calculate geometry, we can calculate parameters, thermodynamic flow parameters on this impact. However, what we saw theoretically, I will just make a small drawing here, is a very simplified case. So this was our analytical calculation case when we had shock wave and flow impacting, okay, for example, this horizontal flow, or sorry, flow with some inclination impacting on a wall. We saw just a point where it reflects from a wall. In a real case, there is a boundary layer, and the presence of boundary layer changed significantly this impact picture. This picture becomes much more complicated, complex. First of all, because boundary layer by itself has structure which cannot be solved purely analytically, right? In the most simple case, we need to solve system, or at least one differential equation, ordinary. But in a general case, it should be a system of partial differential equations and cannot be solved analytically. And then we have this shock wave impacting on our already complex boundary layer structure. And this flow is also compressible. Many physical processes, compressibility, turbulence, also starts to happen. Flow separation creates very complex tasks to be solved analytically. So such tasks cannot be calculated in an analytical or simple numerical way, and can be solved in a numerical simulation or experimentally. First of all, before talking about structure of such flow, I would like to tell about necessity, or why we are so interested in such effect, and if it's important, and when it's important, when it's not so much important. First of all, such a process of impact of shockwave on real wall always happens. So it's always present, cannot be avoided in real life. At point of impact, we have so-called separated vortex or locally separated flow. Here in this zone is creating a vortex. And flow velocity in this zone is almost equal zero. It means that temperature will be very high. Temperature would be equal to stagnation temperature in this zone of recirculation. We must have a material strong enough to resist this temperature. Before this flow separation, temperature can be significantly lower, and after this separation, temperature, okay, or gradient at least, is not so high. Temperature by itself, I think it will remain high for a long distance, because once you heat flow inside this vortex, this heat will be transferred by diffusion, for example, or by processes of mass transfer in convection along this boundary layer. This is why important to know where it happens, how big is this effect, which exactly are flow properties at this point, which are pressure and temperature loads at this point, in order to create a structure which would sustain successfully this problem. Right? As I told you already, this problem always happens, so must be solved in any case when you have impact of a shock wave on the wall. This picture can be different for different angles of shock wave, for different Mach numbers, but in general, you can see on this figure 40 how it happens. Right, for For example, normal shock waves also can happen such a problem, and in such case we have so-called lambda shock wave. This lambda shock wave looks like this. Okay, we have shock wave which is split and has 2 feet, for example, like 2 small feet, and disturbed boundary layer around. It's quite difficult to say about, or no, probably I made the legs too small, like this. Boundary layer and 2 shock waves separated. It's very similar to lambda Greek letter, so it's so-called lambda shock wave. Happens when normal shock wave meets perpendicularly the wall. It's another type of shock wave. We will talk about it after we talk about nozzles. At the end of chapter 10, we have a specific topic devoted to such kind of shock wave. But returning back to our case, this oblique shock wave hits wall with some angle. What happens? Here at zone where it approximates to boundary layer, we see huge gradient of pressure, huge gradient of all flow parameters, right, and change of flow direction. Okay. Flow velocity. Shock wave is also supported by change of flow direction. Cannot be different. So probably here we will have inclined flow, and then we will have again inclined flow when it changes. It's after the last shock wave. What happens in the middle is a number of compression and expansion waves depend on the structure of this flow. We can find acceleration and deceleration flow in the middle. But let's go back. Flow, our shock wave hits boundary layer and reflects. It reflects not from the wall. In this case, it reflects from a boundary layer, because inside boundary layer we have a relatively low velocity, and for external high velocity flow, such a boundary layer looks very similar to a wall, okay, because velocity inside boundary layer is small. In most part of boundary layer is small. So we have sudden change of flow, sudden change of flow velocity, thermodynamic parameters, and flow direction. And because of this, we start to have flow separation, and starts to appear this locally separated vortex. Since we have a vortex inside boundary layer, such a boundary layer grows. So it like expands and becomes bigger, like a bubble. Inside this bubble, we have locally separated flow. Because of this, shape of boundary layer changes, okay, and the reflection of this shock wave also changes. So flow adapts to shape of boundary layer. Initially, it may be different, right? When you start to calculate or simulate transient flow with the initial distribution of flow parameters, you will not see a bubble. But then when the shock wave hits wall, you will see bubble appearing. Bubble, I mean the vortex, okay. Appearing and growing inside boundary layer. At some moment, there is a balance between flow properties in this region, and the picture becomes stationary. After some growth, okay, this growth is fast initially, then it becomes slower and slower and slower. At the end, this growth stops and bubble remains here. There are also other shock waves in which we might see some reflected shock waves. there is an induced separation shock wave is a reflection of partial reflection of main shock wave. And then when we have flow after bubble, also our shock wave, our boundary layer is changing its shape. And because of these changes, all compression waves we have here at this lower zone, they unite and they form an additional so-called reattachment shock wave. So these reattachment shock waves are initially formed by a number of compression waves, which you may see start from boundary layer. Then this induced separation shock wave is meeting with reattachment shock wave at some specific point. They will intersect because they have different flow properties, they have different inclinations. They are not parallel, they are never parallel. They will meet definitely, and they will form a strong shock wave. So this is what we see at the end. This is why when we make a picture, small scale picture, make a zoom. When we see a global picture, like I draw you before our analytical flow, this flow separation can be seen right here. Okay, this small I draw on the upper figure is this very small zone, very small boundary layer. Something like this we can see in a simulation or inside experiment. Inside the experiment. So here we have our shock waves accumulated and reflected shock wave. So what we calculate analytically is actually relation between angle of a shock wave, flow properties when flow is reflected, and the angle of reflected shock wave. Reflected shock wave, which is already accumulation of all disturbances in the flow. So globally, our model, our analytical calculation is correct. We know correctly how to calculate big picture, right? Bigger picture. But when we go in details, when we go in a small scale calculation, we see a very, very complex picture, and this small detail can never be calculated analytically, can be simulated. And I think when you are doing simulation, it's very important to note when you are simulating your diffuser, definitely shock waves will be reflected. You need to take into account that such a flow picture will exist or should exist on your simulation. Such a problem can be simulated. I think we will still talk about it in future chapters. I think there is a discussion about turbulent boundary layer and shock waves, where I will show you some pictures, some recommendations on mesh and several where you can improve or quality of simulation, or at least calculate your simulation with a good accuracy. Here, Anderson shows an example of simulation and experiment. I show you relation between position of flow changes from figure 940 and flow properties. Usually we compare or validate flow simulation and calculation by two parameters, which are pressure on the wall or pressure distribution on the wall, can be measured experimentally with some step, as you may see on figure 41, and shear stress. It's part B on figure 41. Pressure is much simpler to calculate and to measure there are many experimental points we may see, because each experimental point is a single orifice where we have a small tube which goes to pressure sensor. So experimentally, very easy to measure pressure. You need just to make many holes and connect to pressure sensors. When we are talking about shear stress of tau W, is W means wall. Okay, so shear stress on the wall is harder to calculate or to measure, because needs a sensor which measures this parameter, which is not small. It occupies some space, so there are very few points on experimental curve of shear stress. Okay, but pressure is easy, right? This PW by P0 means pressure on the wall divided by stagnation pressure on infinite distance, right? P0 infinite. We are not referring here to P0 at the same point, because at each point P0 is changing. Flow is not azeotropic, so reference stagnation pressure should be outside of non-azeotropic region. It means infinite condition, P0 infinite, far distance. Source for reference. It's a very initial discussion about this question. I hope we can return to it in future, especially to calculation of this problem. There is no unique or universal calculation method. Each model we use, or CFD model or analytical model of this process, is giving very different results. So, but I think the reference could be for us experimental data, right? Closer is your simulation to experimental data, better is quality of simulation in this particular zone. It can be also a problem when we compare to experimental data, because not all experimental data converge. For example, once we will analyze pressure distribution, like shown on figure A, with respect to experiment, it's usually very nice, very good correspondence of experimental and numerical data. But when we will analyze shear stress, in such case, we might find many problems and huge difference. The only conclusion we can make from here is that this problem of interaction of shock wave with the boundary layer is so complex that nowadays there are no reliable methods to calculate numerically shear stress for such a region. Is it good or bad? It's up to you to decide. But I think since usually this zone is very small, reflection zone is very small, contribution to general error is not so big, and we can have small errors inside very little zone of impact of a shock wave. And in general, we receive good results where this impact is not present. So I hope it's clear that for many physical processes, which are complex physical tasks, we cannot find an appropriate numerical model or CFD model, and we cannot calculate some tasks numerically. We cannot simulate. This is quite normal, and I hope in future these problems would be solved. But there is no prevision when. Simulation is complex. Please let me know if you have some questions. I will need to open another presentation. just a moment. But meanwhile, you can tell me if there are some questions. Today we touch very superficially this question of interaction of shock waves and the boundary layer. I think it for introduction is enough, but you should understand just it's a top part of problem, right? Of iceberg. We just see very small piece of this problem. There are books on interaction of boundary layer with shock waves, many books. There are many dissertations, doctorate dissertations made on just topic of impact of shock waves on boundary layers. So it's quite advanced questions, not just because it's short and small region. Okay, small region, but this small region could help us to understand a big problem. Okay, I'm trying to open next subject. Okay. Just give me a minute. And if you have questions on a previous problem, you can type. Okay, I would like to continue today with chapter 10, which is talking about compressible flow through nozzle, diffusers, and wind tunnels. I will start explain about nozzles today, and next time I think we will be already making some calculations which you will need to perform in work 1. I hope after next week you will already have all information to finish computational part of work 1, just 1 month before delivery deadline. Also, I remember now that next Tuesday we will not have class because I have a meeting with Reitor, and I would recommend you to read this part in a book and see videos related to calculation of nozzles. I have several, including examples of nozzle calculation. So I hope it will be useful. And in class, we will meet only next week on Thursday, if all goes as I think. Okay, so nozzles, part of nozzles. Everybody knows what is nozzle, right? We already saw such pictures many times. There are nozzles of different types, and main application of nozzle is to create thrust in a rocket, where we have oxidizer and fuel on board, and we burn inside combustion chamber, releasing heat energy, and inside nozzle we transform this heat energy and high pressure flow to force and thrust, accelerating this flow, reducing pressure. There are some specific points in the nozzle. We might see inside combustion chamber velocity is usually assumed as 0, so 0 velocity. So in because of this, we assume Mach also 0, and pressure equal to stagnation pressure, temperature equal to stagnation temperature. I would like to remind you that stagnation parameters are happening in case when flow is stopped. Flow has no velocity, theoretically, analytically, no velocity. Of course, in real life, flow always moving. But you already know that if flow is moving with very small velocity, pressure and temperature are very, very close, extremely close to their stagnation values. Then we have acceleration. Some part of the nozzle is subsonic, where Mach number is smaller than 1. This acceleration happens because area is reducing, right? At some moment we have incompressible flow, then we start to have compressible flow after Mach 0.3. I hope you remember why flow starts to be compressible, because density changes with change of pressure. And at the critical point, throat or garganta in Portuguese, we have Mach 1. Okay, Mach 1. It means flow reach its speed of sound. And then we have totally different behavior of nozzle. It starts to expand. And expanding nozzle, we continue to accelerate flow, Mach more than 1. Accelerating more and more, we gain more and more thrust. Thrust is a force which acts against drag. To accelerate our vehicle, we need to create thrust. We know that there are nozzles for different types of engines, not just for rockets, but also for airplanes. And not just for airplanes, right? There are even flying cars nowadays, I think. And the principle is same, that high temperature, high pressure flow is accelerated inside convergent and or inside divergent nozzle, depending on type of flow. Okay, first practical supersonic wind tunnel. Supersonic wind tunnel is a wind tunnel which has supersonic flow conditions in its test section. This test section you can see here on this screen is in the middle, this circular part. There is a window to observe, and we can see during the test or camera can film flow pattern. If, for example, Schliering method is used, can visualize shock waves, visualize flow structure. The supersonic wind tunnel is designed by same principle as a nozzle. This is why it's discussed here. It has a section of convergence. It has throat where Mach reaches 1, and it has the divergent section where Mach accelerates. Such a wind tunnel is usually very heavy. It requires a lot of power to operate. Also, to create some certain conditions of flow, it must be adjusted. So this is why we can see here several actuators. It could be mechanical, electrical, or pneumatic actuators, which allow to change flow. They also can be combined with pressure sensors or some instrument which are used to control flow properties. As we may see in future, creation of an appropriate profile is extremely important. This profile of convergent divergent section is very important because we do not want to have shock waves or some pressure waves or disturbances inside test section. Inside test section, we want to have supersonic flow with preferably uniform flow distribution. Such flow can be created only adjusting all points inside nozzle, which accelerates flow. There are many requirements to this. I think in a section of linearized supersonic flow and method of characteristics, it will be more clear why we need to adjust this geometry. Okay, this is an example of supersonic wind tunnel. Usually it's a heavy structure. It can occupy one building or several buildings, for example. In Poland, we saw supersonic wind tunnel with the test section of approximately 50 centimeters, which occupies 3 buildings, similar to buildings of FGA. So, for example, some size of campus is just a wind tunnel because it requires a lot of hardware, it requires a lot of power, requires air storage, requires power plant, and additional equipment to provide experiments. So it's usually very, very expensive and very, very big hardware, which not many institutions can have nowadays. Okay, this is what I was talking. This is a subsonic wind tunnel in Institute of Aviation of Poland in Warsaw. It's a closed circuit wind tunnel. Okay, and the turbine we can see, which accelerates air. This is test section of approximately 10 meters size. And this part is a supersonic wind tunnel. This wind tunnel was built yet in Soviet times. It has a standard design. And there were many such wind tunnels in Soviet institutions built since Poland was making a part of Soviet camp. Also, such a tunnel was installed at this Institute of Aviation. How it works? It has 2 tanks. You can see 2 spherical tanks, each 1,440 cubic meters with the pressure, high pressure. You need to pressurize air because to accelerate just air from atmosphere is very hard. You need enormous power. So it's much more practical to store this power in advance. We store power inside pressure of tanks. Okay, and then when test starts, these valves open and air comes and goes inside. Just a moment. I will change color, it will be more visible. So air comes here, goes, returns, comes inside through the nozzle inside test section. Test section is here. We can see 2 people observing experiment. Building is not so small as it's shown here. It's just schematic. I think this building is huge. It's huge. Not I think. I saw all this equipment. This building is huge. Then nozzle section, a block of several tons. I don't know how many, but there are rails. You can see them here. Rails which move in a different position. They substitute one nozzle to another. When you need to test with different Mach number, you change the nozzle section, and you need to use rails. There are several test sections we may see, okay, on this screen. there. Then there is a test section with all the equipment, and then flow goes, returns, and recirculates. Some part of this air would be discarded to atmosphere, will be thrown to atmosphere because we need to always to accelerate, to add additional energy to this flow. So more air is taken from high pressure tanks and added to main flow. So we always add air from tank and we throw some excess of air to the atmosphere. In such a way, we supply our flow with energy. There are also many other additional equipments in all this history. For example, another building here is a power plant, which does not just produce an electrical energy, but also produces or compresses air. Right? It produces energy and compresses air inside these huge tanks. And there is a pool to cool down this equipment. Okay. All energy goes to heat at the end. We know, right, that all energy is transformed to heat. So we need a pool with to accumulate our heat from test equipment. If you are interested on the website of Institute of Aviation, I think all these materials are available. I found them very, very interesting and exciting. Nowadays, this equipment is all updated, is not old, like it looks like. Okay, structure is not new, but it has all modern equipment for analysis and test and measurement. So it's controlled by computers. It has a lot of computational power to analyze flow in real time, many sensors, quite advanced measurement techniques. And this is something that we always would like to have, but I do not believe that someday will happen that we will have, unfortunately. Let's be realistic. This is here a test section. You can see here, this test section is disassembled to mount experiment. When you need to mount experiment, you disassemble test section, install hardware inside and assemble back. And the nozzle part also is moving here, the nozzle part. I don't know why it's here. Maybe we switch nozzle and test section, or I made photo from another side. These huge air tanks. These tanks are bigger than building. You can see here on side to store building. I think it's another laboratory, and the tanks are much, much bigger than the size of the building. I think it's the size of 3 or 4 floor building. Test section inside, since it's a supersonic wind tunnel, it cannot be very fragile. It cannot be thin or light. Since it's a huge energy used to pass flow and size is big, all these parts are made of very thick metal, very heavy metal. And there are a lot of heavy stuff there. This particular part here, I think it's an adapter for to install the test body or airplane or other test body they have. There is a quite old control equipment we might see here. It's but it's it should not confuse you, because okay, all this test facility is old, right? And they decided to keep this interface, let's say, but behind all this interface, there is all new digital equipment. So it's very nice. You can see here alpha, which is angle of attack is changing, right, with different values. P is pressure, and I think it's a pressure in the test section or something like this, and some other control equipment we have. I don't know actually how all this works. We never saw it working. We just had an excursion and saw it as a demonstration, not working. But I like a lot that visit. Some bodies for testing inside this wind tunnel. It's an airplane model. This airplane model is very, very nice. It's made of solid metal. All these models are made of solid metal, cannot be different materials. And if we, for example, measure distribution of pressure on wing or measure distribution of some parameters, usually just pressure, right, on temperature, there are holes. There are holes and there are pipes. You can see here a model of the wing for testing. So if we need to know pressure distribution, there are holes, there are pipes, and this wing is then connected to airplane. So quite interesting, right? Quite interesting. If we have many points for measurement, number of tubes can be also very big, should be big. Okay, I recommend you one day to visit such a facility. Not maybe in Poland, but to visit to know what is supersonic wind tunnel. It's very interesting. There I just show you very small part of our visit, because it's not possible to show everything, to explain everything, how it's look like. It happened 6 years ago, and I hope one day we can visit again. So returning back to chapter of the book, we are discussing inside part 2 questions, nozzle flow and diffuser flow, and at the end we combine these two definitions and discuss about supersonic wind tunnels, because wind tunnel is always a combination of nozzle and diffuser, something that accelerates flow and something which decelerates such flow. Okay, I hope we have enough time. Equations for quasi-one-dimensional flow. Why quasi-one-dimensional flow? Because in usual one-dimensional flow, area is constant, as you can see on figure 6a. For constant area, we have distribution of thermodynamic and flow properties just as a function of x. In quasi-one-dimensional flow, we have also change of area as a function of axial coordinate, and we have change of other flow properties, thermodynamic and flow and velocity, as a function of x. We do not see say vertical component of velocity. We will see just horizontal component of velocity everywhere. This is an assumption allowing us to elaborate quasi-one-dimensional flow when flow is still going according to one-dimensional structure, so it has just one velocity component, but same time this flow has variable area. You can ask, okay, how flow is changing? Oh, sorry, how flow is changing in the middle? There is a flow direction which is not purely or is horizontal, and the answer is the following: that of course in the middle flow is not horizontal, and there is a vertical component of velocity, of course. But when we are applying control volume approach, we will see as control volume all this volume you can see on figure B, and at the entrance we have just horizontal component of velocity, same as at the exit we have just horizontal component of velocity. vertical component of velocity will happen somewhere in the middle, which is not taken into account by shape of control volume. So it's like a black box. You can see something happening inside according to system of equations we have, right? But we do not see in details. We see just entrance and exit of this control volume. In both of them, velocity is horizontal. So in the middle, we do not see horizontal velocity. Equations describing flow in the nozzle. This is control volume. They are continuity equation, momentum equation, and energy equation. We assume that flow is isentropic, so stagnation enthalpy is constant. And to complement our equation system, we need the enthalpy and equation of state, definition of enthalpy and equation of state. Combining together, okay, re-expressing, combining together and applying to control volume of size, infinitely small size, dx, or we apply it to finite element, let's say, or small control volume with the size dx, we see on the entrance parameters, thermodynamic parameters of pressure, density, we see area on the entrance and velocity. At the exit, we will see same parameters with some increment. E by dp plus dp, a plus da, area, velocity, and density are also changing at the exit. And then these two quantities we use, we apply to our model presented on the right side of the equation. So just on the for P1, U1, then ρ1 and A1, we use just these values, and for cross-section 2 for this model, we use values on the exit from control volume, and then we receive equation. We receive equation, which you can see right here. Oh, all these three equations are shown, but the final one is on the lower right part of this screen. Then, after we receive this equation, we can apply to it some relations. Let's see, which are some relations? For example, isentropic relations, and we transform from velocity and density to Mach number. Since we can rewrite Mach number as function of velocity and density, we can find, as you see on this formula here, right? We can write it in terms of change of area and change of velocity. dA by A is differential of area by area, and du by u is differential of velocity by velocity. In this whole history, Mach number enters just as parameter without any kind of change or differential. This is one of the fundamental equations for nozzle flow. It says as relation between change of area and change of velocity. How it can be used? For example, let's see this first case. Area is decreasing, but Mach number is subsonic. If Mach number is subsonic, m squared minus 1 is how much? Is smaller than 1? Okay, smaller than 1, so it's negative. Sorry, smaller than 1, smaller than 0. Smaller than 0 is negative, and it means that dA by A is changing differently with respect to du by u. Means when we decrease area, we increase velocity. In opposite, when we increase area, we decrease velocity. This case here, dA by A is more than 0, velocity area is increasing, and according to our equation, du by u is decreasing. And same logic we can apply also to supersonic part. M squared minus 1 is positive, bigger than 1. It means that dA by A here is more than 1. It means that du by u is also, sorry, more than 1. Oh, sorry, more than 1, more than 0, positive. Sometimes I confuse 0 and 1. I think it's something like some problem which I have. I will try to fix. Same thing for decreasing area. dA by A smaller than 0, so area is decreasing, and it means that du by u is also smaller than 0, not 1. 0. And this formula giving relation between change of area and change of velocity, as I told you, is extremely important to understand reason why velocity is increasing in supersonic flow differently with respect to subsonic flow. Okay, definition of nozzle and diffuser. Very fast and very simple. Nozzle is a structure which accelerates flow from subsonic, becomes sonic, and becomes supersonic. Diffuser is opposite. Diffuser can be supersonic, then sonic in the throat, and subsonic at the exit. Okay. Nozzle and diffuser are different. Now I have one question to you. Probably I will not. I cannot give you equations today. Probably we can leave solution of that area velocity equation for next time. But I would like to question you one thing. Think at home. Maybe you find an interesting answer on my question, or at least it would be nice to think about. So, question is the following. We have a nozzle. Okay, we have supersonic nozzle, we have supersonic diffuser. They both have same shape, as you can see on picture 10. Having same shape, it means that behavior of air should be similar, but it's not similar, right? But for both of these cases, inside throat, we have Mach 1 in nozzle case, and we have Mach 1 in diffuser case. So we have same shape, we reach same condition. It's not just Mach 1, if is equal 1, it can be also pressure, same, and can be also temperature and density, same for both of these cases. So all same flow conditions. My question will be the following. Why in case A, flow accelerates, Mach more than 1, and in case B, flow decelerates? Please think about this question, and we can discuss it. We can start next time from such kind of discussion. I would like to remind you that flow properties in the middle are same, and geometries are absolutely same. So we can start absolutely from same conditions in both cases. We can discard this initial part. It's not important absolutely, because we already reach same flow properties. Starting from these flow properties, we can start calculate. But flow goes completely different in case A and case B. Next time, I hope to hear some of your answers. If you are very lucky, or if you know, or if you find in literature, please let me know. I think it would be an interesting point to discuss. We meet next Thursday, Tuesday no class because of a meeting, and please read instead of lecture, please read the book and see previous videos which I already recorded about this question. Thank you very much and see you next week. Have a nice weekend. Goodbye.